Welcome back to the Deep Dive. Today, we have a bit of a mission, I think. We want to cut right across the standard hype cycle of artificial intelligence.
That's a good way to put it.
We're not here to talk about, abstract promises. We are here to trace a really tangible, rigorous pathway. Our goal is to take these genuinely complex technical concepts, we're talking specifically about transfer learning, and trace their entire journey.
Right, from the very beginning.
From the academic foundation all the way through to scientifically validated, peer-reviewed, and, well, often life-saving applications in the real world.
And that's the critical distinction, isn't it?
It feels like it.
What you're seeing summarized here, it's not just theory. It's a detailed methodological journey where we're combining foundational concepts, things you'd learn in an undergraduate setting.
Okay, the basics.
The basics, but then applying the rigor you'd develop during, say, deep doctoral work, and then pushing those limits even further into postdoctoral research.
So it's a whole academic journey put into practice.
Exactly. The whole process emphasizes that building these advanced AI systems is, a documented, rigorous process. It's about learning, building, and this is the most important part, validating.
Validating against what?
Against real-world data and, crucially, external scrutiny. It's a craft, not magic.
That makes the structure of this deep dive absolutely essential then. So we've broken it down into two very distinct but interconnected parts for you. First, we're going to lay the groundwork. We're calling it the foundation of learning.
Makes sense.
We'll unpack the core concepts like transfer learning and detail the specific, and I mean highly accessible technical stack, the tools that make these complex systems buildable for, well, almost anyone today.
Almost anyone, yeah. The barrier to entry has dropped so much.
Then, we're going to pivot hard. We'll move to the validation of practice.
This is where it gets really interesting.
This is where we stop talking about prototypes and start analyzing real scientific articles. We're talking error metrics, confusion matrices, peer review, the works.
The real proof.
And we'll be diving into two fascinating case studies: advanced classification systems for venomous snakes and a modular conversational AI designed for health informatics. You'll get to know them as SnakeChat and RoboDoc. Okay, let's unpack this cornerstone concept then, transfer learning. We need to define it without, immediately burying ourselves in machine learning jargon.
Sure.
I like to start with an analogy to make it intuitive. Imagine you spent years learning to read English. The alphabet, grammar, syntax, the whole deal.
You have a solid foundation.
Exactly. Now you need to learn to read a super specialized academic journal on, say, particle physics.
A very niche topic.
A very niche topic. You don't have to relearn the alphabet or how sentences work. You just need to, fine-tune your existing skill to add a new set of vocabulary and context.
That metaphor is perfect. It really encapsulates the efficiency of the technique.
So how does that map to the technical side?
In technical terms, transfer learning leverages what we call pre-trained models. These are the giants of AI systems you've heard of, like MobileNet for computer vision, or the big GPT series for language.
So those are the expert readers in your analogy.
Precisely. Think of them as the expert reader.
And why are they considered experts? What makes them so powerful?
It's the sheer scale of their training. They've acquired immense general knowledge because they were trained on these colossal data sets. We're talking millions, sometimes billions of data points, images, text, code.
And that takes a huge amount of time and resources, I imagine.
Months or even years using massive computational resources that most people just don't have access to. So they've already learned the fundamental patterns.
What kind of patterns?
Things like what edges look like in an image, how textures relate to each other, what basic objects are, or the depth structures of language. When we do transfer learning, we borrow that knowledge base. That's the frozen part of the model. We exploit it.
So if we borrow that colossal pre-trained brain, what exactly is the adaptation layer we're adding? What's the new work we have to do?
You're just adding the specific specialized intelligence, the cortex, tailored to your unique problem.
Okay.
And this is usually done by adding or just replacing the final layer of the neural network. We call it the classification layer.
So give me an example.
Okay, so MobileNet already knows how to detect shapes and patterns from millions of images. Instead of teaching a model what a coral snake is from absolute scratch,
which would require a ton of data.
A ton of data. We take MobileNet, which fundamentally knows what stripes, scales, and geometric patterns are, and we just fine-tune it for our new specialized domain, like telling apart dozens of similar-looking Brazilian snakes.
And you're only training that last little piece.
Exactly. We train only that final layer, or maybe the last couple of layers, on our much smaller specialized data set. The rest of the model, that core knowledge, it stays frozen and unchanged.
That structural choice, freezing the foundation and only adapting the very top layer, that sounds like the key to making this all so accessible and fast.
It is.
What are the big practical advantages this gives you? Especially for, an independent researcher or a small team that doesn't have a huge tech budget.
There are three, and they are absolutely critical. They fueled this whole explosion of accessible AI.
Okay, what's the first one?
The first is data efficiency. And this is probably the most revolutionary part for specialized fields like medicine or biology.
Why there specifically?
Because in those fields, getting massive data sets is incredibly hard. But since the model already has general knowledge, it knows what a stripe is or how to identify the silhouette of a lung. You're not teaching it vision from scratch.
So you need fewer examples.
Significantly fewer. You don't need millions of images. You might only need, say, dozens or a few hundred really good examples for each class to fine-tune that final layer effectively.
And that changes the whole timeline.
It's the difference between a multi-year data collection project and maybe a few weeks of preparation. It's massive.
Okay, so data efficiency is number one. What's two?
The second is cost reduction. This is the direct result of the first point, because you're only training a tiny fraction of the network.
That final layer.
Right, that final layer. The computational demands just plummet. You don't need access to massive server clusters with GPUs running for months. You can just leverage the knowledge that's already encoded in those pre-trained models, which are often free and public. It just fundamentally changes the economics of it all.
And the third advantage?
And finally, it's just speed. You're capitalizing on all this existing knowledge, so you deliver robust, high-accuracy results much, much faster.
So the whole cycle gets shorter.
The time from a concept to a viable, high-performing model shrinks from months or years of training to potentially just hours or days of fine-tuning. And that rapid iteration is essential for science.
This combination of speed and cost reduction, it just naturally leads us to the biggest paradigm shift in the whole industry, right?
Yeah.
The democratization of AI.
Absolutely.
For so long, building anything cutting edge meant you had to be fluent in specialized languages like Python and have access to all that heavy-duty computing power.
It was a very closed-off field.
But that is changing so fast, and it seems like the key driver here is the API, the Application Programming Interface.
The release of public APIs, especially for the large language models, the LLMs from places like OpenAI, that was the moment AI stopped being a fortress. It completely changed the relationship between a developer and the technology.
How so?
Before, if you wanted an AI application, you either had to build the entire house yourself from the ground up, or you bought a finished proprietary product. There was no in-between.
And now?
Now, the LLM providers offer the core intelligence as bricks.
Bricks, I like that.
Yeah. Independent developers and researchers are given these foundational components, the ability to converse, to reason, to understand context without ever having to train that core AI model themselves. So small teams can focus entirely on their special application and how to integrate these pieces.
And this shift is mirrored exactly in the architecture and the tech stack used for the studies we're looking at, SnakeFace and RoboDoc. You're moving away from that traditional Python-heavy world.
Yes, that was a very deliberate choice.
Tell us about those specific technical choices, particularly the reliance on JavaScript and this thing called TensorFlow.js.
Right. So the foundational choice was to move away from Python. Now, Python is dominant in machine learning research, no question, but it often creates these bottlenecks when you try to actually deploy something.
What kind of bottlenecks?
Communication between the back end and the front end, managing different environments, it gets complex. So this research focused on JavaScript, and specifically TypeScript, which adds that extra layer of rigor and safety with typing.
And what's the big advantage there?
It's efficiency and simplicity. You're using a single language, JavaScript or TypeScript, for everything. For the machine learning itself, which is handled by a framework called TensorFlow.js, and for the web application, using something like Angular.
So no more split teams.
You drastically simplify the complexity. You don't need a team managing a Python backend that has to talk to a JavaScript frontend. You just need expertise in one unified stack. It lowers costs and speeds up deployment.
Okay, I get the simplicity of one language, but the truly revolutionary part seems to be where the computation happens. If you're doing real-time image classification, doesn't that still need a powerful server?
It absolutely used to. That was the old way. But TensorFlow.js changed that. It allows the pre-trained models and that fine-tuned classification layer to run directly in the user's browser,
On their own computer?
on their own computer, often using the GPU on their device. This enables what we call decentralized computation.
And the implications of that for scalability must be huge.
Think about it. If 1 million users suddenly decide to classify a snake photo at the same time,
The server doesn't crash.
there is no central server to crash. The computational load is distributed across all 1 million of their devices. The researchers don't have to maintain or pay for expensive high-performance servers to handle that traffic.
That seems perfect for public health applications, especially in places without robust infrastructure.
It is. It's ideal. Plus, there's a massive security benefit, which is crucial when you're dealing with sensitive data, like the medical images in RoboDoc.
Ah, because it's all local.
Since the model runs and processes the data locally, the actual data, the X-ray, the eye scan, the patient's measurements, it never leaves the user's browser. It offers a level of privacy that centralized server models really struggle to match.
And this stack also lowered the barrier for just rapid testing and iteration,
Right.
thanks to tools built on TensorFlow.js, specifically Google's Teachable Machine.
Teachable Machine is a fantastic example of the accessibility this whole shift created. It's essentially a no-code environment built right on top of TensorFlow.js.
What does that mean, no code?
It abstracts away all the tedious, repetitive parts of the transfer learning ritual. Things like uploading images, augmenting the data, pre-processing, setting all the little hyperparameters, monitoring the training. It handles all of that for you.
So you can focus on the data and the problem?
Exactly. The researchers use Teachable Machine a lot for developing the first models in the SnakeFace project. It lets you build a state-of-the-art image classifier in an afternoon without writing a single line of complex machine learning code.
It really democratizes the building phase then.
It does. It separates the model training from the application development. So a researcher can update a model on the Teachable Machine site, and that change is automatically pushed to the Angular app through a simple link. That ability to rapidly prototype is invaluable in fields that are always changing.
So if someone with some basic web development knowledge could build a high-accuracy image classifier in a few hours with these tools, where does the real work actually begin?
You've hit on the philosophical message of this entire journey. Everything we've discussed so far, understanding the concepts of transfer learning, mastering these efficient tools like TensorFlow.js, recognizing the possibilities of APIs and no-code platforms, all of that is crucial. But it is unequivocally preparation.
And I think that distinction gets lost so often today. People see a working app and they assume it's a scientifically proven solution.
Exactly. Building a prototype or a functional app demonstrates feasibility. It shows that the concept can work, under ideal conditions, but feasibility is not scientific proof.
It's not validation.
It is not validation that your approach is robust or reliable or even the best way forward. That proof only comes when you take that method and you submit it to the brutal, rigorous scrutiny of real-world data, real-world noise, and critically external peer review.
The YouTube demo versus the peer-reviewed journal article.
That's the perfect analogy. The scientific community demands quantitative metrics. Error graphs, confusion matrices that show you exactly where your model is failing, and accuracy metrics from diverse, messy data sets. Mastering the tools is the preparation. But only rigorous, validated application is scientific progress. Without that second step, you just have an interesting toy.
That sets the perfect stage for our pivot into part 2. We have mastered the bricks, we understand the power of transfer learning, and this efficient JavaScript and API stack.
Yeah.
So now let's look at the houses that were actually built with this method. The validated, published, and peer-reviewed systems that are solving really urgent, concrete problems.
Right. We're looking at what happens when these established, efficient techniques, transfer learning, TensorFlow.js, are intelligently combined with that cognitive leap you get from modern conversational AI from the OpenAI APIs.
And the results were applied to some tough fields.
Very challenging domains, yeah.
Yeah.
Tropical biology and health informatics.
So why the intense focus on peer-reviewed articles? Why can't we just, trust an impressive demo video?
Because peer review is the only process that enforces accountability and real rigor. External experts, people who actually study snakes for a living or who are radiologists, they critically analyze your methods and your results before the paper gets published.
So they're checking your work.
They challenge your data collection, they question your training process, they force you to publish the real numbers. They don't rely on a subjective feeling of, oh, the AI is smart. They use hard metrics to show exactly where the system works, where it excels, and just as importantly, where its limitations and weaknesses are.
That transparency is key.
That transparent vulnerability is crucial if you want to build a system that's safe and trustworthy enough for the real world.
Okay, let's start with the biological imperative.
Mhm.
Our first case study is SnakeChat. It's a conversational AI designed for snake classification, which is, it's a matter of life and death in places like Brazil.
It really is. The source data shows over 27,000 snake-related incidents a year in Brazil alone.
And getting the correct antivenom serum depends entirely on getting that initial identification right.
It does, and the focus here was on a truly critical scenario, telling the difference between the highly venomous true coral snake, Micrurus corallinus, and its almost identical but harmless mimic, the false coral snake, Erythrolamprus aesculapii.
That sounds like the ultimate test for a vision model.
It is. It's a classic case of mimicry. In a scenario like that, a mistake can be fatal. If you misidentify a venomous snake as non-venomous, you're making what's called a type 2 error, a false negative.
And the cost of that error is huge.
Immense. Delayed treatment or no treatment at all. So the challenge of separating these visually similar species, especially from a low-quality photo taken by a panicked person in the field, that challenge drove the core architectural decision of the whole system.
Which was what?
To reject the idea of a single monolithic model in favor of small, highly specialized components.
Okay, so why reject the idea of just building one giant model that can classify all 400-plus Brazilian snake species? Wouldn't more data just make it better?
That's the common assumption, but it's often flawed. We call it the big model problem in specialized fields.
The big model problem.
Yeah. While large general models have broad knowledge, they inevitably lose accuracy per class as you add more and more classes.
So they get diluted.
They get diluted. Global performance might stay high, but the accuracy for that one specific life-critical subset, like the coral snakes, it becomes unreliable. The model becomes a generalist, but it's not precise enough when precision is absolutely mandatory.
So the SnakeFace researchers decided to break the problem down into smaller, high-stakes chunks.
Precisely. SnakeFace used multiple small, highly specialized transfer learning models. For instance, instead of one model for all snakes, they might train one model just to tell the difference between 5 visually similar types of false coral snakes.
So it has a very narrow job.
A very narrow, specific job. Another model might be trained only on the complex Bothrops genus of pit vipers. These small, focused models can maintain extremely high accuracy, often up to 98 or 99%, because their task is so well defined.
But that creates a huge logistical problem, doesn't it? How does the system know which one of these little specialized models to use? If I upload a picture of a pit viper and it sends it to the coral snake model, the result is going to be meaningless.
It would be. And that is where the LLM glue becomes absolutely indispensable. The entire system is unified by the OpenAI API, and specifically by its advanced function calling feature.
Okay, so the LLM is the dispatcher.
The LLM acts as the intelligent central dispatcher. The user uploads an image. An initial analysis is done, often using GPT-4 Vision to generate a rich text description of the image.
And the LLM reads that description.
The LLM receives that description, it taps into its huge global knowledge base about snakes, and then it decides, based on that text, which specific high-accuracy SnakeFace model or models it needs to call.
So it's making a judgment call first.
It deduces the most probable category first. Is it slender with bands? Is it thick-bodied? Where is it found? And then it delegates the final, rigorous visual classification to the most appropriate small model. The LLM provides the reasoning, and the specialized models provide the proof.
That sounds like a really elegant fusion of general intelligence and specialized accuracy. But when you combine two fundamentally different types of AI, one is deterministic, one is stochastic, the research found some really interesting challenges.
It did. The contradiction comes from the nature of the parts. The SnakeFace transfer learning model is deterministic. You give it the same image 5 times, you get the exact same probability output every single time.
Predictable.
But the LLM, the OpenAI API, is fundamentally stochastic. It's designed to be a bit randomized to give slightly different, though similarly intelligent, responses to the same input.
And when those two systems clashed?
When they clashed, the LLM's stochastic nature sometimes introduced noise. It might second-guess a correct, highly confident prediction from SnakeFace, which occasionally led to a final answer that was confusing or just unnecessarily vague. Managing that tension is a huge research challenge.
And then there was this phenomenon you called the reasoning flaw. A kind of hallucination where the LLM argues itself into being wrong. Can you describe that?
This was one of the most fascinating observations. We saw that LLMs really struggle with rigorous deductive reasoning, especially when the information they're given contradicts their own internal biases.
So what happened?
In some test cases, the LLM would get a text description of a snake, say, 3 white rings, 4 red rings, and a conflicting classification from the SnakeFace model. Instead of accepting the deterministic visual fact, the LLM would just generate this elaborate, perfectly written, logical-sounding argument to support its own initial guess.
Even if the guess was wrong.
Even if that guess was demonstrably inconsistent with the color description it was given. It was a perfect, coherent story built around a fundamentally wrong conclusion. It showed us that these models are brilliant text generators, but they are not flawless engines of logic.
That sounds pretty dangerous in a biological context.
Yeah.
But you also found the system could sometimes act smarter than its individual parts. Tell us about that key example, the one with the Oxyropus rhombifer, the Amazon false coral snake.
This was the moment where the power of this integrated approach really shone. We tested it with an image of an Oxyropus rhombifer. The LLM, based on the general look of the snake, initially guessed coral snake.
So a false positive for danger, a type I error.
A type I error, right. It then called the specialized SnakeFace models. The specialized false versus true coral model correctly identified it as Oxyropus rhombifer, but a second, more generic model misclassified it as the true venomous Micrurus corallinus.
So now the LLM has 3 conflicting pieces of information.
Its own wrong guess, 1 correct classification and 1 incorrect classification. And here's the crucial part. The final synthesized conversational response it generated managed to integrate this conflicting data brilliantly.
What did it say?
It said, with perfect clarity, the snake in the photo is most likely an Oxyropus rhombifer, also known as the South American false coral snake. However, it is often confused with the highly venomous Micrurus corallinus, or the true coral snake, which has similar coloration.
Wow. So it didn't just give the right answer, it gave the critical context.
Exactly. It gave the context needed for a user to understand why confusion exists and why they should still be careful. It showed a level of intelligent synthesis, a kind of conversational hedging that's far beyond what any single visual classifier could ever do. The LLM used its language skills to acknowledge the conflict and add biological relevance. It proved the whole premise.
The beauty of this architectural approach, these small, low-cost models coupled with an LLM dispatcher, is how generalizable it is. And the research showed this by applying the exact same method to healthcare, creating the Robodoc conversational AI.
That's right. It proves the core concept is domain agnostic. The transition was fundamentally pretty straightforward.
Why so straightforward?
Because we were just replacing specialized knowledge in one domain, biology, with specialized knowledge in another, health informatics. The underlying structure, the LLM using function calling to delegate tasks to small, high-accuracy models, that stayed exactly the same.
So what kind of models did Robodoc integrate?
It was a diverse suite. We used transfer learning models trained on medical images. For example, one model was trained on chest x-rays to tell the difference between bacterial and viral pneumonia.
Which is a critical distinction for treatment.
Critical. It determines whether you use antibiotics or just supportive care. Another set of models focused on eye conditions, using OCT scans. These are highly detailed cross-sectional images of the retina to identify things like drusen, which are early signs of macular degeneration.
And it wasn't just image-based models, was it? You also integrated text-based classification.
Yes, to show true multimodality. We integrated a text-based neural network model for diabetes prediction.
And why a different type of model for that?
Because the input data for diabetes, risk, BMI, age, glucose levels, it's small, structured, low-dimensional data. So you can use a shallow neural network. It doesn't need the depth of a big vision model. It's super efficient. It takes in numbers and outputs a risk probability. But to the LLM, it's just another tool it can call.
And this structure completely changes the user experience in medicine, doesn't it? It moves the interaction away from clunky forms to just natural language.
It really does. The LLM acts as an intelligent assistant, handling what we call parameter extraction and output interpretation.
So what does that look like?
A doctor or a patient could text the chatbot, I'm 24, my BMI is 35.42, what's my diabetes risk? The LLM automatically pulls those numbers out of the sentence.
It extracts the parameters.
It extracts the parameters. Then it does the critical task. It calls the correct specialized model, in this case the diabetes model, and most importantly, it interprets the complex numeric output like a raw probability of zero point 0.8 and translates that into a human-friendly response, adding context, maybe even suggesting next steps.
And it can handle missing data, which must be a constant problem.
A huge problem. If a user only provides their BMI and age, the LLM knows it's missing, say, the HbA1c level. So instead of just failing, it intelligently asks the user for the information it needs. It keeps the conversation flowing. And it can even integrate other functions, like scheduling an appointment if a high-risk prediction comes back from one of the models.
So on the implications for medical decision-making, the research talks about human noise and variability in diagnosis. What did the models reveal about human expertise?
This connects back to a lot of foundational studies in cognitive science. What these computational models offer above all is consistency, predictability. They drastically reduce what we call noise, that unwanted random variability in human judgments.
Even when they're looking at the same information.
Exactly. You can give two expert radiologists the same X-ray on 2 different days and get 2 slightly different reads. The model's prediction is consistent and reproducible every single time. It doesn't get tired or distracted. It provides a more reliable baseline.
But, as you stress with SnakeChat, these models are not perfect. And in a medical context, you have to talk about safety trade-offs.
That is the essential caveat, always. In the pneumonia classification, for instance, the model was highly accurate, but it wasn't perfect. And critically, it sometimes failed to identify urgent, true positive cases of severe pneumonia.
A Type 2 error, a false negative.
Which in medicine is often the most dangerous kind of error you can make.
So how do you mitigate that?
The research highlights that for a clinical deployment, you have to intentionally design the system to minimize type 2 errors, even if it means you get more type I errors or false positives. You train the system to favor safer errors.
So if it's not sure, it should err on the side of caution.
Precisely. If the model is 51% sure it's viral pneumonia and 49% sure it's bacterial, which needs immediate antibiotics, a safety-first model would flag it as high urgency, possible bacterial, which then triggers a human evaluation. You reduce the risk of missing something severe.
So you're not trying to replace the human diagnostician. The model is more like a highly consistent safety net or a triage tool.
That's the perfect way to frame it. The system is an advanced, always-on triage tool or assistant. It reduces the human burden by handling that initial assessment and flagging the high-risk cases. It cuts down on the noise in human judgment, but it still requires the final contextual judgment of a medical professional. The model gives you a powerful prediction. The doctor provides the wisdom.
We've taken this fascinating journey from the efficiency of transfer learning and the accessibility of this JavaScript and API stack, all the way through 2 highly specialized, scientifically validated systems, SnakeChat and RoboDoc. If you had to distill the core takeaway for someone listening who wants to move from just learning about this stuff to actually applying it, what's the single most important lesson?
The core finding is, I think, irrefutable. The solid path to real-world innovation, especially in these very specialized fields like bioinformatics or health tech, is grounded in pairing that foundational learning with rigorous quantitative application.
One without the other isn't enough.
Not at all. The foundational learning, through a course or a formal education, that gives you the foundation. You understand the tools, the architecture, the possibilities, but that's just potential.
And the application.
The peer-reviewed application provides the validation. That's the necessary, brutal testing against real-world complexity and noise. It's where you get the quantitative metrics that separate a cool demo from a reliable tool.
They're inseparable.
Absolutely inseparable. Trying to deploy systems without mastering the foundation leads to flawed, insecure products. And trying to learn without validation just leads to expensive trial and error in the dark. The solid path is right there in the middle, where theory meets testable, peer-reviewed proof.
And it seems like, thanks to this paradigm shift with public APIs, the whole landscape has changed. The cost of leveraging this kind of intelligence is dropping, and the barrier to entry for independent researchers has just crumbled.
Exactly. We're no longer in a world where you need massive centralized capital to build an advanced AI system. Intelligence is now provided almost like a utility, as bricks of specialized capabilities, whether it's the linguistic reasoning from GPT or the vision expertise from a fine-tuned model.
The AI is a service model.
Right. And independent researchers and small teams can use this to rapidly build complex, customized, context-aware applications without that multi-million-dollar investment that was required to create the core models in the first place. That's why we're seeing this explosion of innovation in every focused domain you can imagine.
That brings us to our final thought for you to consider as you wrap up this deep dive. The research we've looked at today, from identifying venomous snakes to classifying X-rays, it shows that the success of complex real-world AI systems now hinges not on a single, monolithic, perfect AI, but on the intelligent integration of multiple, smaller, highly specialized models by a conversational AI hub.
The Lego approach.
The Lego approach, exactly. It allows the whole system to be so much greater than the sum of its individual parts. So given this new modular reality, where the core intelligence is outsourced and the real value is in smart integration, how will this fundamentally change what expertise even means?
That's a deep question.
Is the new expert the person who masters building one of those highly specialized components? Or is the true value now held by the architect who can intelligently glue them all together, manage their conflicting outputs, and design that conversational interface that translates all that complexity into clear, actionable advice in fields like biology and medicine?
A profound shift.
It's a profound shift in what we need to teach, what we need to learn, and where we all apply our focus. We'll leave you to ponder that until next time on The Deep Dive.